Good afternoon, everyone. Today we'll be presenting on the bridge replacement on US 17 and NC 37 over the Perquimans River Bridge that connects the towns of Hertford and Winfall in eastern North Carolina. My name is David Ragan, and this is Nathan Wiggins. And we both work for H&H, or you might also know it as Hardesty and Hanover. And I'm a bridge engineer based out of the Raleigh office. I previously worked for the prime consultant actually on this project, RK&K. And I was there during the pursuit, design, and construction phases of the project. I'm happily fulfilling David Peterson's role today, so hopefully I don't mess it up too bad. While I worked at RK&K, David would often look for volunteers, but we were always so busy there, it would usually be he'd be looking for voluntold. And I don't work for him anymore, but here I am, and I'm still being voluntold what to do. So I'm excited to be here, and hopefully I'll do okay filling in for him. So this project was advertised by the NCDOT Design Build Group. The intent of the RK&K Design Build team was to put together, as David described it, the premier movable bridge project team in the state. And RK&K is known for their outstanding design build success throughout the state of North Carolina. And so they were tasked with the bulk of the civil transportation design work. And this also included the structural and geotechnical work throughout 27 fixed approach bridge spans. H&H, on the other hand, is one of the premier movable bridge firms in the country and was tasked with designing the channel swing span structure. And then Intera Coastal Engineering was on the team for the hydraulic complexities of the project, which required rigorous scour and hydraulic modeling. The design team was paired with McLean Contracting, who has extensive coastal and major water crossing construction projects throughout the country. A breakdown of the timeline and schedule. The team was formally put together in February of 2017 and shortlisted later in April. The proposal phase lasted several months, with the winning bid being opened in November. The McLean team did not actually have the lowest bid price at the opening at around $57 million, but with the strength of the proposal and a technical score of a 94 versus an 89.5, the best value bid order was actually flipped and McLean was awarded the project. The final adjusted price difference came down to less than $1 million. The planning and design was completed over the course of 2018, with the initial test piles being driven in the summer of 2019. And finally, the bridge was opened in 2022 in August. The Perquimans River opens up into the Albemarle Sound in northeastern North Carolina, for those who are not familiar. The project site is along US 17 and NC 37, just north of the intersection between the river and the sound, as you can see in the graphic up on the screen. It is the only downtown connection from the town of Hertford across the river to Winfall. And originally, there was a movable Warren Truss in service at this site. And this bridge was built in 1928 and was part of what was described as the historic S Bridge due to the overall shape of this bridge. So one of the main desires of the project was to replace this part of the bridge in kind to keep that historical aspect of the crossing as well as that S shape. Thus, NCDOT decided to procure the first movable bridge in North Carolina through the design build process. To elaborate on that old movable bridge from 1928, the S Bridge, it had a number of positive and negative features. Mostly it was unique in that it had a worn through truss with a swinging 161-foot span based on a center bearing. The unique characteristics made it historically significant and culturally enduring enough to be included, in fact, in the town's logo. So they're very proud of this bridge. However, there at this point in time, and the modern age, if you will, it had many drawbacks. It had a low navigational clearance that was always prone to flooding, had narrow lanes on a decaying and degrading timber deck. It was graded structurally deficient as well as functionally obsolete. And after years of corrosion and extensive section loss to the main steel members, the bridge was posted at 17 and 24 tons for SVs and TTSTs respectively. Not only that, but with the age of the bridge, as maintenance items came due, the parts were so old that they were difficult to secure, and at times the bridge would have to be closed. for extended periods. And additionally, on the north end, the old bridge connected to an approach causeway that was natural in occurrence. But this causeway was also deteriorating and settling unevenly due to the poor natural soil conditions there. And in fact, NCDOT conducted some subsurface investigations and found voids or holes up to 3 feet deep underneath the roadway that were attempted to be mitigated with concrete fills and asphalt. And so it was quite the matrix of material underneath the actual causeway roadway. So even with how unique the bridge was, the negatives you can probably see vastly outnumbered the positives. So it was time for Ender Bridge. So some projects have special features that are required for the contract, and this bridge was no exception. However, this special feature was a little quirkier or a little different than you might expect it to be. And if you look closely at this picture here, you'll see what is actually the most famous feature of this town, more so even than the truss span and the S bridge, which is a turtle log. And in fact, the turtle is also featured on the town crest right next to the old bridge. So I actually went to fly this bridge and get some aerial photography back when I worked at RK&K. And as you speak to the locals, I can confirm that these turtles are part of the identity and what's important to these actual people that live in the community. So the NCDOT, in cooperation with the citizens, created an actual 40 by 40 foot, what they called a restricted zone, where no construction or bridge could impede upon this area, because they wanted to ensure the integrity of this log and its sunbathing clients, the turtles. Not only that, but they asked and were contractually obligated to build observation platforms. These were built at bent 7 and 11 for the public to enjoy this, I guess, feature within the river. And there was a sidewalk full length of the bridge for people to access those platforms. So the town takes the turtle watching pretty seriously, but if you actually get out there, it's a pretty cool feature that makes it very unique. So the new structure chosen, as I kind of alluded to, was meant to preserve as much of the original as possible due to the historic nature and identity that's associated with not only the truss, but also the S shape. So starting with that S curve, the bridge would end up being 2,691 feet long, 2 12-foot wide lanes with 4-foot shoulders, as well as a 5.5-foot wide sidewalk that I just mentioned before. Not only that, but they raised the minimum navigational clearance up to 15 feet. And most importantly, they required a signature swing span in the navigation channel. So these pictures are just from the in-service bridge, just to kind of show you how pedestrian friendly and open to the community that the bridge actually is, and kind of gives you a sense in real time as the S shape kind of curves you around the bridge. So these are real pictures, not renderings. The 27 approach spans that RK&K designed were lightweight concrete decks on Florida I-beam or prestressed I-beams, which is rather typical, but the substructure was a little bit more interesting. So with the influence of the Albemarle Sound and the bridge being located in a major river, a detailed scour report was conducted by Intera Coastal Engineers to generate a scour bed. The scour elevation was determined to drop as low as -28 feet. So the solution for the substructure foundation was 30-inch square prestressed concrete piles driven down to a tip elevation of -80 in order to achieve the required desired fixity. And these piles were 7.5 KSI in strength and included additional corrosion inhibitors to ensure the quality and longevity of these piles in the river. There are 18 expansion bents along the bridge with 5 plumb piles in each, as well as 7 fixed bents that had 8 battered piles multi-directionally to account for all the lateral loads. On top of the piles were cast in place concrete caps, and the structure was raised above the 100-year flood. And lastly, NCDOT, in fact, required 10 test piles be driven at this project. Here you can see some additional photos from the actual construction of the project. In the top left, you'll see then building the reinforced concrete caps. And to the right of that is the actual finished expansion vent. You can see the 5 plumb piles. In the bottom left, you'll see the fixed vent with the 8 battered piles, as well as the floor to I-beams on top of that. It's an interesting photo for a number of reasons. One is you can see the vast change in elevation between what was existing versus what is now in service. And also you can see the deterioration of the causeway as the bridge is essentially abutted right up to the edge of the roadway. And then the last photo on the bottom right, you can see the actual installation of the piles at the pivot pier for the movable span. And as you look kind of at an aerial view of what the actual conditions are, the tree line that looks like it's out in the middle of the river actually kind of is. That was the natural causeway. And on the left, you can see where the old bridge was connecting to that. And from the previous slide, you could see all the deterioration of that natural causeway. So the actual alignment that was chosen essentially circumvents that causeway and connects directly to the town of Winfall. And again, you can see the elevation change in that photo as well. And with that being said, y'all certainly did not come here to see me. You came here to see David Peterson, but I like to think that the star is actually Nathan Wiggins. So I want to turn it over to him so he can talk about the movable span. Thank you, David. So at that point, like this is a pretty good slide to transition from the fixed spans to the movable span. So yeah, it's a pretty good aerial photo of the old alignment and the new alignment, as well as the pivot pier as they're starting on the erection of the swing span truss out in the middle. So yeah, down here in the middle, you can actually see the new pivot girder as well as some of the stringers that are being installed. So once the pivot pier was in place, the next thing to consider is the swing span truss that would carry the roadway over the navigable channel in the Perquimans River. So to build a new modern span that sort of preserves the look and feel of the old truss, we also went with a Warren through truss. This one is 190 feet long, 41 feet wide. So the lanes are 12-foot lanes, 4-foot shoulders, and a 5.5-foot sidewalk. All of the members are ASTM A709 structural steel rolled members that are all metallized for protection. So the look and color matches the old swing span, as does the truss. The only thing different with the truss is that there are additional sub-diagonal members added for additional strength. We even went with dome head bolts to match the riveted look of the old swing span. So with swing spans, there's different ways you can go about erecting the trusses. The design team opted for an on-site erection of the bridge in the open position. So still the channel was still navigable, but the roadway wouldn't have been ready just yet. So they installed temporary formwork that was in line with the new fender system. So they could build the truss on site and float in the truss members and then build them there. So the thing about a swing span truss is that it has multiple different conditions. So it's got to swing open and then be able to swing close and carry cars across. So when it's in the fixed or closed position for roadway traffic, it essentially acts as 2 separate truss spans, one from one approach to the center pivot pier, and then from the pivot pier to the opposite approach bent. So you essentially have 2 fixed trusses, and shear is not carried over center. So they act as 2 almost independent structures. But when it opens, the entire dead load of the truss is cantilevered off on either side. So the process of erecting on site involves building out from the center with all of the members cambered up so that as they built out, the weight and dead load of the truss members would be such that all the vertical truss members or the ends of all the beams would be vertical once the full weight of the truss steel was in place. And then after that, some of the machinery would get built and installed, and the dead loads of the machinery that were installed on the truss, as well as the sand lightweight concrete deck, would be added afterwards. So as I said, when it's opening and when it's in the open position, it's essentially all of the dead load is cantilevered off to the side, so it deflects down at the ends, both laterally and longitudinally. So there's machinery components that have to raise the ends of the span back up so that it's in proper alignment with the approach roadways. And so the concrete's not poured until afterwards, so that there's not a big bump that cars have to drive over. So here's some pretty good photos from how the truss was built. So on the left, you can see the erection of some of the machinery support members. So the brown line in the middle, that's the pivot girder. It's a 6 foot deep member because it carries the full dead load of the span as it opens, in addition to the weight of the machinery that's mounted to the bottom of the span. Additionally, you can see that the stringers at the pivot pier are of varying depths. They're deeper towards the center because they're carrying machinery loads and have heavy components mounted to the bottom. And then they built out from there with the stringers and the floor system, and then built the trusses on either side and then connected the trusses with the top bracing as they get out to the end. One of the quirks of this design was, however, there's only a 5.5 foot sidewalk on one side. Typically, you have a swing span that's fully balanced in each direction just by symmetry. However, the deck is not symmetrical, and there's more concrete on the side that has the sidewalk. So in order to counterbalance that, we installed a couple of concrete slabs were poured underneath the deck to balance for the sidewalk, so that as the swing span opens, it's fully balanced. It's tough to, account for that precisely during the design phase. So there were a few additional steel plates that had to be added as we were balancing the span during construction. So one of the main components of the structural portion of the swing span is the pivot girder. It's kind of where the operating machinery is mounted. It's where all the dead load is supported as it opens or in the open position, and then while it's closed, it's a structural member carrying live load. So it's a really key component, and we actually had to make sure that it's precisely level on the bottom flange, because that's where machinery is mounted. That's where it rests on the center pivot. So this picture on the right here, that's the center pivot bearing that carries the weight, the dead load of the span as it opens, and then carries some of the dead load of the span in the closed position. And then on the left, that's Stewart Machines fabrication plant in Birmingham, Alabama, where they're welding up the pivot girder before shipping it up to site for erection. So that's a good transition point. So moving from the structure to the mechanical part, or the mechanical portion of the bridge that gets it to open, the center pivot bearing is the key component. So it consists of a concave steel disc that's a spherical concave steel disc that's 90 inches in spherical diameter, that supports a bronze disc, a bronze spherical disc of 88 inches in diameter that rests on top of it. So it's mounted to the concrete of the pivot pier, and that's where the steel disc rests there, and then the bronze disc is mounted to the swing span that moves. So that's where the movement and the support is achieved, and that's what the bridge actually pivots on. So with the concave and convex disc setup, that allows for the dead load of the span to have a tendency to self-center if the swing span is centered where it's supposed to be on the pivot pier. So this is a really critical component of the construction, is making sure that the center pivot bearing is exactly located at the center of where we want the bridge to swing, and also at the center of the roadway alignment above, since it's got the purpose of carrying dead load when the bridge is in both the open and closed positions. So to give a little bit more of a close-up of the discs, this is a shop assembly. That's the bronze top disc in Stewart Machine Shop, getting ready to be lowered for testing in the shop. And then on the right is our drawings of it. So on the left, the drawing on the left is a bronze disc, and that fits down right into the spherical convex of the steel bottom disc. So the next, once the pivot bearing is set on the pier, the next thing is to make sure that the drive machinery and everything else is set precisely to be concentric with and centered on the pivot bearing. So the drive machinery consists of two separate drive units that each have a drive motor, brakes, and an enclosed an enclosed gear reducer to drive the span. And then mounted to the pivot pier, there are two diametrically opposite segments, rack segments, that the drive machinery uses to swing the span open. So after the pivot bearing is set onto the pier, the next step is to set to within 10 thousandths of an inch concentricity to set the drive machinery and mount the track to the pivot pier as well. So both of the machinery drive units are mounted to the bottom of the truss, and then they mate with the gears that are mounted and anchored to the pivot pier. And that's how the driving and operation is achieved through that machinery. So here's a couple of pictures to help show the improvements. So for the mechanical and electrical design, the big thing was improving on what was there originally and designing for resiliency and redundancy. So the original swing span is on the right. And as you can see, it's old and rusted out, and those gears are a lot less robust, have a lot less bearing area for carrying the loads used to operate the span. And there's only one. So the tendency of the gears, there's a radial force as well that could cause the bridge to move around laterally as it swings open. But with the setup with two diametrically opposite drive units, the radial forces are equal and opposite. So the swing span stays centered. Additionally, with two drive units, both are sized and robust enough to open the bridge and operate the span should the other one be out for service or any other reason like that. So there's a bit of redundancy built into the system as well. So it's a big improvement over the drive system from the previous swing span. Another difficulty is in addition to mounting a swing span to that moves to a concrete pier that doesn't move, you also have the issue of aligning machinery that's mounted to the swing span to machinery that is mounted to the fixed pier. So on this picture in the bottom right, or in the picture on the bottom right, that's the circular rack that's anchored to the pivot pier that the drive units will mate with. So making sure that the drive units are straight and plumb and parallel to all the gear teeth was a very iterative process that takes a lot of fine tuning and adjustments, and making sure that the swing span is balanced. So there's also multiple assemblies required to make sure that are required to be aligned to each other. As I mentioned, there's the pinions, which are the gears mounted to the swing span, and then the racks that are mounted to the pivot pier. There's additionally, the bridge would be subject to all kinds of loads, such as wind loading, or could be slightly imbalanced, and all of those things. So there's another set of balance wheels that are installed also on a concentric circle with the pivot bearing, and they allow the pivot, or they keep the swing span from rotating too far, or tipping over in the event that there's winds while it's opening. So there's a number of different components that were that required a lot of iterative adjustment during construction. Additionally, as I mentioned, the dead loads of the swing span are cantilevered out to the side. So there's machinery on the rest piers as well that is required to be aligned and adjusted so that that it lifts the deflected ends of the swing span back up to the precise correct elevation. So here's a couple of pictures of different adjustments and stuff throughout construction. On the bottom right, that's one of the balance wheels. So they're set about 12 feet from the center, and they would resist any of, like I said, any tipping moments from wind as the span opens. On the bottom left, that's it's a difficult thing to get everything balanced. So we were actually adding some concrete counterbalancing weights to the swing span as we were opening. And then in the top right, you can see there's a level mounted to the bottom of the pivot girder in both directions. So it was critical to make sure that everything is level and set and balanced, as well as concentric. And it took quite a number of iterations to get through all of that stuff. As I mentioned, there's the balance wheels, and those are the key component of the support and stabilization machinery. As the swing span opens and also as it's rests in the closed position, there's a number of machinery systems required to make sure that it's supported and stabilized. So the balance wheels, as you can see, they're right up next to the drive units, and they roll on a tapered track to keep the bridge centered and keep it from tipping over. There's 8 balance wheels, and they're diametrically opposite of one another, and they are intended to stabilize the span as it opens. The next piece of the stabilization and support machinery are the center rollers. So the center rollers are mounted on the lateral edges of the pivot girder, and they're essentially just big rollers that roll up onto strike plates embedded in the concrete of the pivot pier. So as I mentioned, the dead load, the lateral dead load of the span and the deflection of the pivot pier has to be raised back up. They also serve as live load bearings at the center pivot pier, and it's a passive system that is just rolled up onto a plate, or the strike plates, as the bridge is closed. So one of the design intents for these, and one of the improvements over the previous swing span, is that it's a passive actuation, or it's a passive raising. Like, you don't have to have it's not driven by any motor or machinery. It just rolls up onto the strike plate. The previous system had wedges that had to be driven through a system of linkages. So there's a whole other set of drive machinery that was mounted to the bottom of the swing span on the old bridge that would actuate wedges at the center, and then wedges at the rest piers. So this is an improvement in terms of robustness. These are pretty big steel rollers, and it also allows for passive actuation. So there's not a second set of machinery mounted to the bottom of the swing span. The next key piece is the end lift machinery. So these have to raise the deflected ends of the swing span a bit more than the center rollers would. The swing span, as I said, it's 190 feet long. So either side is 95 feet. So at the end, the deflection is around 1 3/4 inches or so. So the way that we are raising the deflected ends of the roadway back up into the level of the roadway on the approach spans is there are 4 separate machinery units or drive units at each of the corners of the swing span that have an eccentric roller that as it rolls, it presses up on the strike plate mounted to the bottom of the end floor beam, and acts as
like I said, it acts as a live load bearing, as well as to deflect the ends of the swing span up. So it imparts a positive reaction, and these are all driven with a right angle worm drive gear reducer. So the difference in a worm drive and a normal gear drive is that your input shaft is perpendicular to the output shaft, and it's also it's very difficult to back drive a worm gear. So you have the added benefit of the weight of the bridge and the weight of live loads from traffic are not going to have a tendency to drive the machinery, or it doesn't have to be imparting any kind of resistance to hold those eccentric rollers in place. The way that the gears are set up kind of do that on their own. And then finally, once the bridge is all the way closed, there is another linear actuator that is mounted to the rest pier on either end, and it drives in a lock bar that is designed to resist any of the opening loads or wind loads that would have the tendency to cause the swing span to swing. So it's designed to be very robust and is a final redundant measure to hold the swing span in place. And then finally, the electrical systems were also designed with resiliency and redundancy in mind. Hertford and Winfall, neither of them are very big towns. It's also in coastal North Carolina, right where, as David mentioned, the Perquimans River runs into the Albemarle Sound. So there's quite a large area for a storm to pick up. It's prone to hurricanes, things like that. So power outages are another big consideration. And having someone on site, as far as what the Coast Guard requires for opening and operating the span for navigability of the river, having someone on site in Hertford would be a big challenge as well. So the new control system or electrical system is set up so that there is a redundant, completely separate, identical programmable logic control system housed in Elizabeth City that is about 15 or 20 miles away, where there's another movable bridge. So they can open two bridges with one operator. This also allows for a bit of a redundancy in case there's a power outage at the control house in Hertford. In the case of an emergency, they'd be able to open from Elizabeth City. So this communication from Elizabeth City to Hertford is achieved with a dedicated fiber optic line that's isolated from the internet and encrypted, so that only NCDOT is able to send electrical signals to the bridge, which is obviously a good thing. You don't want someone to be able to hack in and mess with the bridge from the internet or from their computer. Additionally, in the new control house, you can see up in the top right there, the old control house is pretty low to the water. And then on the left, the new control house concrete going up, the elevation is set pretty precisely so that it's above the 100-year flood level, so that any electrical equipment is not at risk of flooding and shorting out and having problems from that sort of thing. Additionally, so the electrical system is really, really redundant. So there's a programmable logic control system, which is pretty standard for movable bridges. And then there is a third control system based on relays, which are a little bit more old-fashioned and reliable in case the PLC systems go out. That's also housed at the machinery house there in the top right. And then all of it is up to date and modern with it's not finished yet, not that picture on the right, but there's a TV screen there, and there's a lot of CCTV that shows all angles of the bridge. It's the control panel is all displayed on HMI screen, so it's all pretty high tech in there at this point. And like I said, it's raised above the 100-year flood line to make sure that everything's robust and resilient in the event of a hurricane or a significant storm event. Additionally, in the event, like I said, in the event of a hurricane or a power outage, there's an on-site backup generator so that the bridge could be operated even if the power in the town has gone out. So there's an uninterruptible power supply such that if the power is cut, it will keep the bridge operating for 20 minutes or provide electricity to the bridge for 20 minutes until the generator can kick on, and then you'd be able to have your power supply from the generator, which is also housed in the control house above the 100-year flood level. So it's ready and operational, even if there's a heaven forbid a pretty big flood event. So that concludes all the big talking points that we had. So as David mentioned, the swing span is pretty important to the town. So we tried our best to build or design a bridge that's robust and resilient and up to modern standards that preserve some of the look, alignment, and key critical pieces of the bridge that's so important to the town. It's so important that they also have it sitting on rest piles just upriver, ready to be installed as the centerpiece for some updates to the Missing Mill Park just off of downtown. So they've got some plans. If you go out to Hertford, there's some renderings of it. There's a big park they're planning to put in with all kinds of picnic tables and events, and they're going to put the old swing span out there for people to still walk on and stuff, because it's a key piece of their town history. It's a big thing for them to have their S bridge still. So I thank you guys for having us, and that's all we've got for our presentation. Will we do like a Q&A kind of thing?
Okay. They don't have any questions for these guys? So the general rate and so the truck is assembled on site.
Yes, sir.
Did they metalize each individual piece before they were shipped to the site?
Yes, sir. Sure. And then I believe there were some additional metallization. There were some issues with it, I guess, where they had to remetalize a couple of spots, some touch-ups kind of stuff on site, I think.
Yeah, I think we have a couple of questions on Zoom.
Oh, okay.
Well,
Go ahead.
I might have missed it, but you talked about redundancy a lot. What was the redundancy for the end lifts? Like if one of those go out with a bridge to go along?
So the redundancy there would be there is a manual operation setup. So it's a lot of the redundancy for older bridges was manual operation, but for these there's a second gearbox that's off to the side that's got a lockout kind of clutch. So if the power went out, they could pop that back into place, and there's actually like a big turning wheel that they would slide onto the end of the shaft, and then you'd have to crank it a bunch of times. Yeah, it wouldn't be fun, but we could do it. Some of the oh, go ahead.
What was the cost?
I don't know the exact specific figure, but I want to say that the construction cost came in at 60 or 62 million.
The word at 57.
It was a little bit over budget, but not grossly over budget, I don't think. It did. Construction did get delayed quite a bit. Obviously, it was right in the middle of COVID, so there were some issues there with getting stuff done. So the original schedule got pushed quite a bit. But I think that the design or the construction cost came in right around 60 to 62 million. So reading.
A question Zoom first.
Did the contractor preferences or limitations impact the design of the movable spans? That is a good question. I think that was probably part of the reason for setting up the drives the way that we did. They're relatively isolated, and it's a lot easier to install the drive unit, so the motors and brakes were installed and aligned and set up as the single unit. So the contractor on site really only had to mount and align two separate units rather than having a full machinery setup where they're aligning shafts and other motors to each other in the field, which is a lot more difficult. I don't think there's anything else that came up from construction that we changed. There was some difficulty. I can speak mostly for the mechanical side of things, being a mechanical engineer. So I may be missing some of the stuff for some of the other disciplines, but with the drive units, it was a bit of a difficult situation trying to mount them to the bottom of the swing span. The output shaft is cantilevered, so all of the loads on the gears to operate the span were cantilevered, and so the stiffness of the frames of the gearbox as well as some of the structures had to be reevaluated during design. But I can't speak for all of the structural decisions or electrical decisions. Yes, sir.
Through the years, it's been difficult to find machinery parts made in America. You
Yes, sir.
buy America calls. How did you deal with that?
Stuff's just more expensive. So the big mechanical piece that is difficult to find by America was the brakes. So there's 2 brakes on each of the drive units. And these at Perquimans, they're pinch Wiggins brakes. So I think there might have been a little bit of a relaxation on by America. I don't know that that's an American manufacturer, but there's not really many American manufacturers making those anymore. And to get people to build outdated models or to update them again, it brings the price up quite a bit. I want to say nowadays it's like 80 to 85 grand or something like that to get a brake made in America, and a lot of movable bridge projects are considering relaxing that requirement on brakes specifically. The remainder of the drive machinery was done at Stewart Machine in Alabama, and then the gearboxes were who made those? They were made in Chicago, tested in Chicago as well. I can't remember. It might have been, I think it was Overton, Chicago here made those. No, it was Bradfoot, but they're out of Chicago. So it was an American company as well. Yes, sir.
Can you explain the sequence of the end lifts and how that works timing wise with the rotation and?
That is a good question. So all the electrical control systems is set up to interlock, so that you can't just push the open bridge button and things start happening. So it's traffic lights and then traffic gates, and then the end lifts would be rotated, and they all have separate drives, so the same signal goes to each of the drives to drive them all at the same time. Otherwise, it would be a bad situation to have them not synchronized in time, but all that's achieved electrically through the control system, so that the end lifts, so it'd be traffic lights, traffic gates, and then the span locks get pulled, and then the end lifts drop, and then you can swing the bridge, and then it'd be the reverse of that going back the other way. And there's all sorts of communication electrically, so that if something did go wrong and one of them didn't drive, you wouldn't be able to continue with the process to have traffic back on the span.
Does the operator one signal and computer sign?
I think for the PLC system that controls everything, so that you kind of have a sequence that it goes through. But I mean, he's there watching everything and has to be aware of it all. For the relay systems, like some of the older system, that's all like he's got to know the process of this button. It's interlocked, so he couldn't. Like one thing won't happen without the piece in the sequence before it being pushed, but for the relay system, it's some has to, know the secrets themselves and go through it. Were there any additional Zoom questions? Yes, sir. So you can probably see it pretty well on the picture. Okay. Sorry. So yeah, so the discs. There's one on the bottom, one on the top that it sits in, and then it's encased in a housing. So the housing is at all the joints. It's gasketed together. There's like a base that it all sits on, and there's a house that actually goes around the two. And it's not all the way tight at the top. So you would essentially have a fill port and then like an oil level glass that you could see where everything, the oil level is. And some of the older ones, you could just pour oil in at the top and then close it back up with a debris shield to make sure nothing gets in there. Yes. Let's see. That might be the fill port right there, and then I think it's on the other side, but on the other side, there's a sight glass to see if the oil level is at a certain point. And during our biannual inspections, for a swing bridge like this, we would take an oil sample and send it off to a lab to make sure there's no contaminants or anything in it. And if there was, we'd flush it and change the oil. I think it's usually it's about on a yearly basis that they flush or change the oil. That's another good question. It's usually like a biodegradable oil, pretty similar to like your motor oil for your car or something like that. It's I don't know the specific numbers or letters off the top of my head, but it's usually got to be biodegradable in case there's a spill because it's over a waterway and there's environmental concerns there as well. But it's not terribly different stuff from like motor oil. Just like, yeah.
Because
I'm fairly certain that it is. I feel like I remember seeing that. Our structural lead time, I think you mentioned that at one point, even though I can't answer that definitively.
I think that's technically by definition would still be considered critical, but they have additional like redundancy to try and eliminate that. But certainly for the in-service live load condition, it's when it opens, it's obviously sitting on the one pivot beam. So, but it's not in service. So, I forgot, but they got some rounds.
Okay. So in the paper we presented this at a conference before, and in the paper we put together, I do have that the swing span truss. So from the pivot girder and all the main truss members, except for the stringers, are fracture critical. So the pivot girder itself, and then I think most of the stuff in the floor system, aside from the longitudinal members, I think would be fracture critical.
Let's say, like, by definition, but they put some kind of state things together. So
Yeah.